Alright, we're back to our logarithmic equations. I have one more example that I wanted to do. So I'm picking it back up. This is where we left off in the previous instructional video in this section. And it is a review problem, so you can see why I would like to do it. First things first here, I noticed that I have the same exact logarithm here. So that would give me 2 log base 9 of x minus 7 is equal to 1. That's going to give me the log base 9 of x minus 7 equal to 1/2 if I divide both sides by 2. Now I'm going to change this to exponential form. Nudge it right up there. I have x minus 7 is equal to 9 to the 1/2. X minus 7 is equal to 3, because that's the square root of 9, and so x is equal to 10. If I plug 10 back in, I'm going to get positive amounts, so that seems like a pretty legitimate answer. All right. In this example, I have to use the formula that we've discussed already about compound interest. And it says determine how long it will take $8,000 compounded monthly at 6% to double. Round to the nearest tenth. So what I'm going to do to double means 8,000 is going to go to 16,000. My amount is 16,000. My original principal is 8,000. 1 plus my interest rate R is 6%. So in this case, 0.06 divided by n, which is the number of times it's compounded in a year. Since it's compounded monthly, it's 12. And then this would be 12 times t. It says round to the nearest tenth. Since I'm solving for time here, it's going to be to the nearest tenth of a year. I'm going to simplify this stuff in here, but before I do, I'm going to divide, well, maybe in the same time, the same step. I'm going to divide both sides by 8,000. And I have 2 is equal to 1.005 to the 12t. I'm going to take the natural log of both sides. I like to use the natural log. I'm going to bring my power out in front, switch the sides. I'm going to get 12t, the natural log of 1.005 is equal to the natural log of 2. I brought the exponent out in front using my powers property for logarithms. I'm going to divide now both sides by 12, the natural log of 1.005. 1.005. And the 12s will cancel, and the natural logs, the expressions will cancel there. And so now I just have to take the natural log of 2, get my calculator out, and divide it by 12 times the natural log of 1.005. And if I'm not mistaken, I remember this to be 11.581. Of course, that's an approximation. This is in years. So to the nearest tenth, it will take about 11.6 years to double the money. It's supposed to be a double. Double the investment. Oops. There we go. It's a little sloppy. Hopefully you can read that okay. Now, when I do problems that have to do with doubling time, especially interest problems that have to do with doubling time, and that's what this one was, there's like a shortcut that you can do to use as an approximation, kind of check your work to see if it's in the ballpark. And it's called the rule of 72. And I have that up here. The rule of 72 says that if you have R percent, so like in this case R percent, this was 6%, so R was 6, and you divide that number R into 72, so 72 divided by 6 is 12, that would approximate the doubling time at that interest rate. Well, 12 years and 11.6 years aren't all that far off, so that's probably a good check. Now, I have one more example here that I want to do that has to do with intensity of sound. It says, suppose the sound of a leaf blower is 115 decibels. Use this formula here, L equals 10 times the common log of I divided by I sub 0 to find the intensity of sound, okay? Which is in, if I'm not mistaken, I think this is something like watts per meter squared for intensity. Okay, the variable L represents the loudness of sounds in decimals, and I sub 0 is 10 to the negative 12. So if I want the intensity, I'm solving for I. So what am I going to, or actually, what am I doing here? The sound, yeah, okay, so I have L is 115, L is 115 equals 10 times the log of I divided by I sub 0, which is 10 to the negative 12. Now I have a 10 out here in front, and I'm solving for I, so I'm going to have to divide both sides by 10. So that would give me 11.5 equals the log of I all over 10 to the negative 12. Well, let's see. This is a base 10 logarithm. So I'm going to bring it over here. I'm going to write this, see if I can do this here. 10 to the 11.5 equals the log, oops, actually got rid of the log by doing this, which would equal this expression I divided by 10 to the negative 12. Multiply both sides by 10 to the negative 12. 10 to the 11.5 times 10 to the negative 12 is equal to I. So I'm running out of space here. I would be equal to 10 to the, add the exponents, negative 0.5. So that would be 1 over the square root of 10. I'm not sure what that is. Thinking it's about 0.3. Probably wrote it down somewhere and I've just forgotten where it's at. But I'm thinking it's probably about 0.3. So I'm going to approximate this as 0.3 watts per meter squared. Okay, might grab a calculator and double check that. That's a 3 there, not a very good one. All right, that's a decimal point right there. Now, it says here, if the threshold at which sound becomes painful is 1 watt per meter squared, what is the intensity of sound from the leaf blower, is the intensity of the sound from the leaf blower above the threshold of pain? Well, no, not if it's got to be 1, so this is 0.3, so no. However, I'm sure that there are a number of rock concerts that will give your ears a testing. And I'm going to throw this one out to Nazareth and Ted Nugent, 1977. My ears buzzed for about 3 days after that concert. All right, so try these problems, practice, practice, practice.